Should be starting right now. And Scott, I think when I started recording, it might have kicked. I might have closed everything.
Looks like you have to agree. It looks like there's an auto shut off of microphone and camera now. So you click one of those, and then you have to click OK that you accept being recorded. Sign your life away.
Sorry about that.
It's all your fault, Cody.
Did not think it would do that.
It's just updates to Teams. You did everything right, don't worry. It's a brave new world of privacy that we live in.
Mm-hmm.
Scott, try to click on your microphone or your camera, and maybe when you try and unmute one of those, it might give you that notification acceptance. Worked for me on mobile, but I don't know if it's the same for laptops. Anybody else on the call have any advice for Microsoft Teams here?
For me, it just it worked when I unmuted and clicked agree.
Are you on a laptop?
Yeah.
Okay. Of course, Scott, we get everybody on early to try to work through these things. Thank you, audience, for your patience while we work through this.
Yeah, this is the first time I've actually seen that second step for the authorization.
Yeah, it looks like it just got implemented recently. Usual hiccups. Scott, would you mind maybe just getting out of Teams and trying to come back in? Maybe if we admit you fresh, it'll give you the option. We're sorry.
Yeah.
The perfect time to play an advertisement for GDIT, the company with IT in its name. Can't quite get it working.
Okay, let's see.
Well, Nancy Delanoche is on from our ACT-IAC leadership. While we're waiting for Scott to come back in, Nancy, did you have any updates besides ELC that you wanted to raise to the quantum community here? Put you on the spot. If you can come off mute. And maybe we blocked everybody.
It might have.
Anybody else able to, Joe Reddix or anybody, could you come off mute just to let us know that you can talk?
Yeah, I just unmuted
AJ.
and that seems to work. I had a little pop-up that said that you have to agree to it and I just clicked yes.
Okay. And I see Randy said he couldn't, or she couldn't. Hey, Scott's back.
Okay. Hopefully this will work. It apparently does not work from the desktop app. You have to use the browser.
Interesting.
All right.
Sorry, Scott.
No worries. Learn something new every day. Hang on. Let me figure out how to share now. Okay. Hopefully you all can see this.
We see it.
Sure can.
Okay.
Looking good.
All right. Thank you all. Teams is lovely. Anyway, Scott Buchholz, lovely to see all of you virtually. For those I don't know, I lead our quantum computing exploration efforts here at Deloitte Consulting. We have a number of people around the globe who've been actively investigating what quantum computing means for us and for others for a number of years now. So I thought what I would do is share with you a little bit of context about quantum technologies, a little bit of where we see quantum computing potentially being used today and tomorrow, and then a little bit of what we're seeing about the workforce as we move forward. And then hopefully there'll be enough time, I'll open it up for questions. So with that, let's get rolling. So the first thing to note is that when we talk about quantum, when we use the word quantum and quantum technologies, it's an umbrella term. It actually covers probably a dozen different things or more. It's a little bit like saying AI. It almost doesn't mean anything. So we like to think of it in three big buckets. The first big bucket is computing. So this is where we're using quantum mechanics, the properties of particles and atoms to actually do useful computational work to solve problems. We're talking about sensors. It turns out that some of the technologies that we use to build quantum computers, and sometimes the failed technologies to build quantum computers, make really good sensors. And those sensors have really interesting properties, sometimes in terms of power consumption or sensitivity or other sorts of things. And so there's an entire field of people figuring out how do we take these sensors and turn them into commercial reality. And finally, the idea of communications. As many of you may know, future quantum computers may be a threat to security, and we have a variety of techniques, both software and hardware, that benefit from some of these ideas that enable us to better secure communications today and tomorrow. So this is mostly going to focus on quantum computing. I'm happy to take questions about any of the other things in the end. The first question I think many people have is, what is a quantum computer? I think the first thing to know is, although on some level the analogy that a quantum computer is a supercomputer is a reasonable place to start, it is not simply that a quantum computer is a supercomputer. We have this idea sometimes. I talk to people who tell me, oh, I've got so much data, I've got such big problems, I can't solve them today. So a quantum computer will be able to solve them because it's like a super duper supercomputer, right? And the answer is actually maybe, but not really. And so how should you think about what is a quantum computer? Let me first start by saying, by giving you a little bit of an analogy, which is today's computers, the classical computers, what they're doing to actually do calculations is they're doing a lot of math. So everything we see around us on our phones, on our laptops, in our servers and in the cloud, there's a ton of math that's happening really, really quickly. And we've been able to do amazing things in the world because we've had 60 or 70 years of the smartest people in the world figuring out what we can do with math. Quantum computers use physics. And maybe this is best illustrated by an analogy, which is to say, if you think about blowing a soap bubble, for those of us who remember being children, right, you get the little soap bubble wand, you dip it in the soap, you blow through, and a sphere comes out the other side. If we wanted to use classical techniques to model what was going on, we could do a quantum mechanical simulation, we could do a ton of math, we could model the individual water molecules and soap molecules. We could put them all together. We could spend a whole lot of time and burn a whole lot of computing time to realize that they were going to form a sphere. And if we did it at the right level of detail, that would probably take us a couple of months on a supercomputer. Yet soap bubbles form almost instantaneously when we blow them in the real world. So one of two things must be true. Either soap film is a mathematical genius, the likes of which we've never seen before in the world, or it just works differently. And the answer is soap film is using different principles. It's using the ideas of physics. And it turns out that you can use physics to solve certain types of problems that are very difficult to solve with math. And then there are problems that are relatively straightforward to math that are not particularly tractable to physics. And so this is where the interesting conundrum comes, because quantum computers are more like this physics engine. It's a new way of doing calculations. The challenge is that while we have decades of experience knowing what we can do with math and classical computers, we're still going through an evolutionary journey to figure out where are going to be the best places to use physics and quantum computers. And in fact, how can we actually apply those technologies to the problems we have today? So that's sort of a little bit of an overview of why it is that quantum computers are interesting and different. If we think about a little bit of the history and how we got here, quantum computers were postulated, depending on sort of your point of view, in the 60s to the 80s in various different ways. But the basic idea was, because, as I talked about with my soap film, it takes a lot of math to do accurate modeling of the atomic and subatomic realm. Richard Feynman, the Nobel Prize-winning physicist, said, hey, instead of trying to do all this math, this hokey math, to actually figure out what's going to happen, maybe we should just use atoms, because atoms are more likely to be able to model one another. And if we can figure out how to make them do some useful work, then we can make all of this come together. Fast forward, maybe a decade ago, people started actually figuring out how we would build some of the basic building blocks of this technology for quantum computing and started stringing things together. Where we are today is IBM has one of the most powerful supercomputers in the world, or at least one of the ones with the most qubits, the qubits being a basic measure of capacity of the computer. It's about 436 qubits. It turns out this is a technical marvel. These things exist often running at temperatures colder than outer space, or with other crazy technologies and ways of actually getting things to cooperate. So it turns out building these things is fiendishly difficult. These are engineering marvels. And for the time being, they are also largely research machines, because while they do the exceptional and the extraordinary, we still have a ways to go to actually make them useful, by and large, in production applications. There is a sister technology, for the sake of argument, called quantum annealers. And quantum annealers are special purpose machines whose job is to solve optimization problems. It turns out that because they are focused uniquely on solving optimization problems, as opposed to being these general purpose quantum computers, they can do a lot more. They are easier to build, and they're actually useful in production today in some use cases. And so we'll talk a little bit more about that. There's some interesting things going on there. When we look forward, however, we see this idea of quantum advantage. Let us not call it quantum supremacy. It's not really clear what that means. But what we see when we look at the roadmaps of many of the vendors out in the community, people are announcing that somewhere in the 2, 3, 5-year timeframe, they anticipate being able to build machines that will actually allow us to demonstrate business value. So we'll see if they're able to meet those roadmaps. But in the meantime, we are on a journey where the capacity is getting better, the quality is getting better, and we're starting to be able to envision what sorts of things might we be able to do with these machines when we get there. So the challenge is, if you think about exponential technologies, there's sort of this classic idea that existing technologies are going along at some maturity curve. And in this picture, that's classical computers, which are continuing to improve. And you can sort of think conceptually about that purple line as being that path of improvement. And exponential technologies tend to mature on a different type of growth curve. And that's represented by the thick blue line. So why is this important? Well, if you think about how digital cameras overtook conventional cameras, there were the initial digital cameras were actually ignored in part because they didn't work as well as the film cameras. And then people started finding places where having a not so great digital camera was better than having a film camera because it was better than the alternative. And what happened over time was we went from having film technology be ubiquitous to having digital technology become ubiquitous as it became, in that case, clearly superior to what was going on. Not always the best analogy because quantum computers are likely to continue to work with our classical computers for the foreseeable future. We are likely to be in a world where we have CPUs and GPUs for special graphic processing. We're likely to have AI processing units and all sorts of specialized processing units and quantum processing units. So we'll be going along, we'll find a very complex calculation, we may hand it off to the quantum computer, get the result back, and keep going. That's the most likely scenario that any of us can envision at the moment for a variety of reasons. So where are we today? We're at that little arrow at the bottom labeled today. And you can see that we have not yet crossed the line where there are things that can be done by a quantum computer that cannot be done classically. If you think about the next couple of years, there is likely to be that little triangular window under the curve, right? Where the blue line in this picture crosses the purple line. And while the space between where the quantum computers can do things that are difficult or impossible to do classically, or they show some advantage to what can be done classically, is small, it is likely to be real. And that's where we start talking about quantum advantage. It's not entirely clear exactly where that lives, but we have some glimmerings. And so I'll tell you a little bit about what we think and hypothesize, and we'll go from there. Another thing to think about, by the way, just to make this an eye chart, is in case you thought that quantum computing was a simple topic, let me help disabuse you of that notion. So there are at least 6 or 7 or 8 different modalities of ways of building quantum computers that people are exploring today. As I talked about, some of them are running systems at temperatures colder than outer space. Some of them involve zapping atoms with lasers thousands, tens of thousands, millions of times a second to try to get them to cooperate. There are a whole bunch of different techniques that people are trying. There are new ones being developed every day. This is not an exhaustive list. And when you look at the notion of maturity at the top of this, I would say it's a little notional, but what it is a reflection of the fact that some of the technologies further on the left have been around longer, have more proof points, for example, of what they can do. As you get further to the right, it's not that the technologies are perhaps going to take longer to materialize, but they might have less organizations working on them. They might have less knowledge base around them. There are other technologies besides, not even on here. And so this is just to give you the sense that there's a lot going on. There are hundreds of startups working in this space, and it can be a complex place to navigate if you don't know where to start. Now, we can talk about how all of this stuff works, or we can talk about, given what I've told you, where are the places that we should all go look in our organizations to try to figure out whether or not we can make this stuff useful. And this is a little bit of an idea of places to go and look. And they start at the left with things that are all around security and communications. We have technologies that enable more secure communications that exist and are rapidly evolving. And those are things worth exploring, particularly for the especially paranoid. And even in some cases for the not so paranoid, there are changes over the horizon that we will be seeing in terms of the way we encrypt and secure data in the coming year or two that all of us will need to pay some degree of attention to. When we start talking about enterprise use cases for quantum computing, we think about things like optimization. I told you that some of these use cases are available today. Quantum annealers are particularly good at solving very large problems, very large optimization problems. You can think about you are a major retailer and you have a fleet of trucks that have to deliver things. You'd like to do so in a way that minimizes the number of trucks and minimizes the amount of fuel you have to use, right? That's a really complex optimization problem. Those kinds of problems are things that become more tractable in some cases using quantum technologies. There are other examples besides. I'll talk to you briefly about one of them, but there are a lot of things in that space. Next, we get to this idea of machine learning. It turns out that as near as we can tell collectively, quantum machine learning trains to higher accuracy on less data than classical machine learning. Lots of reasons why, but that becomes a really interesting place for us to look for potential use cases in that area under the curve. So maybe some of them are optimization, and maybe some of them are in this area of machine learning. And we can think about what might be the characteristics of problems where quantum machine learning might actually generate some advantage relative to the other techniques we have available to us. Further out in the timeline, we have this idea of chemistry and material science. I talked to you about the original motivation for creating quantum computers, the idea that we can do a better job modeling nature with nature than with math. And when we think about that, people have ideas like, can we create bespoke drugs? Can we, so basically drugs targeted to me and my condition as opposed to generally? Can we create new chemical substances? People talk about discovering the next Teflon or improving chemical processes so that we can create green energy with less effort. Lots of different things going on here. Fascinating group of topics. A lot of these things are interrelated, so we can geek out for longer. As I tell people, I'm happy to talk about this stuff longer than all of you are willing to listen. That's probably a true statement. So let's just say this is a little bit of the universe of things that you might go look for when you think about where might quantum computers be used. Here's an example of something that's available today. One of the things that a number of organizations need in financial services, in the government, in a number of other regulated industries like insurance and elsewhere is the ability to generate explainable AI. So models where we can explain the decision. A lot of the technology used to do that is an approach called a decision tree. And it's not, the details are probably not as important as understanding that a human, a mere mortal, can look at a decision tree and actually explain why it took a particular decision, which isn't always the case with the neural networks that we tend to use in more complex problems. It turns out that we can use some of these quantum technologies in special ways to actually create better decision trees than what we can do with our best classical techniques. So in most cases today, if you're a bank and you need a fraud detection system for your credit cards, and you need to be able to explain to your regulator exactly why this transaction was selected and not that one, you're probably using a decision tree. And it turns out we can use some of these quantum technologies to generate higher quality, more compact decision trees. That means that they're cheaper to run, they're more accurate in terms of results, and it actually makes it simpler for them to explain. So it's kind of a win-win-win. And in fact, we can do it in a way that doesn't impact dramatically the pipeline that is typically set up to actually train the models and then deploy them to production. So that's exciting. And this is one example of a number where we can actually use some of these technologies in creative ways to solve problems of today. Okay. In the universe of things that we can do, here is a short list. Some of these things are longer term, some of these things are nearer term, and this is by no means exhaustive. We can think about, if we think about life sciences and pharmaceuticals, you have problems that range from optimization problems and scheduling problems and production problems to and logistics problems to things that look like drug discovery and understanding chemicals and finding like molecules. There's this whole spectrum of things that you could do that are likely to be enhanced by quantum computers. Similarly, finance has a whole range of problems tractable to quantum computing, whether it's this idea of fraud detection, like I was talking about, or anomaly detection, which is sort of the fraud community's nice word for something that looks a little unusual. So everything from that to complex asset valuation and building index portfolios and all sorts of other things where you're talking about either things that are complex time-based calculations, you're talking about things that are complex optimizations, lots of different possibilities in that space. For the government, there are a myriad of potential use cases, and they range from everything from dealing with optimization in the battlefield to dealing with optimization of the workforce to thinking about machine learning problems writ large and sort of everything in between. Because I think, as we all appreciate, the government does all of these things and more. And so there are a lot of potential use cases across industries. And like I said before, this is just a small sampling. We actually spend time working with organizations to help them think about, let's inventory the kinds of things that we might be able to use quantum technologies for. What we often find is when we're going through that list, a number of those problems actually can be tackled by AI and machine learning today or other technologies. And so it's not that because we come up with a list, suddenly we now have to wait for quantum computers. In many cases, we can make some or dramatic improvements on the way things are being done today, while waiting for potentially even better improvements at some point in the future. And so I would encourage all of you, if you haven't spent some time thinking about where some of these technologies might be used, to start looking at places that they might be useful in the future. Okay. Now, this is going to take a little bit of explanation, but let me start by saying, in our experience, and I've confirmed this with others, it often takes a year or two to take somebody who is trained as a classical data scientist, who is trained in today's technologies, who's even a physicist or a mathematician, and train them to start becoming a quantum information scientist, somebody who understands how to use the quantum computers and other technologies to actually go from I can run the Hello Me program to being productive at what they're doing. There are lots of reasons for that, and that's in part because the technology is incredibly complex. The technology is incredibly complicated. There's a lot going on. As I mentioned before, there are a million ways of doing this. There are lots of nuance and all sorts of other things. It just takes time. By the way, if you think about the amount of time I just told you it takes, and you think about what I told you about a number of the vendors' roadmaps, it starts to become clear that all of us are going to need to get on this journey sooner rather than later, because there's a time delay to actually thinking about how to get people ready. And there is a bit of a speculation as to when the technology will be ready, when we'll start seeing that little triangle under the curve. Okay. As humans, when we think about what is the workforce we're going to need in the future, we often look at the workforce that we think we need today and project forward. Human beings are really good at straight line projections. We're very bad at things that change exponentially. And so if you go look at a lot of the workforce surveys, what people will say is, oh, we clearly need more quantum physicists because we can see that there's a demand for those who actually understand how to build the hardware. And by the way, that's true. And you can see people saying, oh, we need, researchers and other sorts of techniques, and that is true as well. What I think is sometimes hard to appreciate is the future is likely to look dramatically different than the world of today. And a good way of explaining this might be to think a little bit about the movement that we've seen between the 1960s, when some of the first classical computers were created, to where we are today. And if you were to be able to look far enough back in time to the 60s, what you would see is there was a very small workforce working in this space. It required people with very highly specialized skills. In fact, there were a whole lot of people with PhDs and other things because the technology was finicky and it was really hard to understand. Over time, what started happening was that group started hiring more people who looked like them, more physicists, to be able to scale things up. And what also started happening is they started going from things that were used for research to things that needed to be used in the real world. And you started seeing engineers show up. Engineers being the people who are most capable of taking the crazy ideas the researchers have and making them repeatable and hardening production lines and making it so you can make them repeatedly and quickly as opposed to crafting everything by hand. Over time, what then happened is you started to see this new breed of person show up called developers. And those folks actually started figuring out not just what was going on and how to build this complex hardware and then write some stuff on top of it, but actually mostly focused on what we can do with the machines. We started to see the languages of COBOL and Fortran and a number of other things where there were higher level constructs that enabled more people to be able to access the technology. And what's happened since then is we see this explosion of a need for developers. If you look around today, there are still researchers, and it's clear that we have more people doing research into silicon and classical computing and all of the things that it can do than probably existed in the workforce in the 60s by several orders of magnitude. We continue to have a need for thousands or tens of thousands or hundreds of thousands of engineers or more who take the ideas that some of these researchers are refining and devising and turning those into the operating reality that gives us teams and it gives us meetings and all sorts of other things. And then as we look forward, right, there has been this whole need for developers that has exploded beyond the need for any of those other things. And I think the analogy in this case, this is a really long explanation for a short analogy, which is we are likely to soon be entering the world where the demand for quantum information scientists starts to explode. As the technology starts to become more accessible, as the technology starts to come together and we start seeing business value, you can reasonably anticipate that the number of organizations who will be competing for the sparse group of talent in this space is going to look a lot like the race that we've seen in the past decade to hire data scientists. All of this to say, if any of you have teenagers like I do, we should all be encouraging them to become quantum information scientists so that they can be in demand in a couple of years. And I say this somewhat glibly, it's also actually kind of true. And moreover, for those who are in the government, it's important to start thinking about how do we create the incentives, not just to have more PhDs and doctorates, not just to have more engineers, but how do we start encouraging the creation of the rest of the workforce we're going to need? And by the way, that's not just quantum information scientists. That's the technicians who have to monitor and repair the cryogenic fridges that keep some of these things cool. That's going to be the people who need to develop the next generation of lasers and laser control systems and everything else that makes all of this stuff go. So super interesting, great news, lots of job opportunity, something to talk with your kids about or to take up yourself. And so, you know, as you think about that, right, getting the workforce ready is going to require all of us to take a bit of a longer term view. For those of us who are in commercial organizations, it means thinking about how do we start getting the existing workforce aware? How do we make sure that they have the right resources, education, training, the abilities to use it, and particularly the ability to collaborate with others who are working in this space. For those of you who are, you know, in the university community, this is really rethinking some of the curriculums that we're teaching and making sure that we're actually preparing the workforce of the future, not just the workforce of today or yesterday. For those of you in the government, this is, you know, similar to commercial organizations, thinking about how do we go harness the passion of the people in the organization who are already looking at this to be able to then amplify their efforts. The reason I say that is I would submit to you that any organization of a reasonable size already has somebody who, as a side hobby, has been playing around with quantum computing. When we look around Deloitte, we've found hundreds or thousands of people who are actually already playing around with the technology, trying to figure out what it means on their own. And what we've found is when we harness those efforts and when we give them some degree of direction and structure and training, that we can actually harness a lot of that effort into improving things in the future. So all of us need to start getting ready for this transition. It doesn't necessarily have to be a huge effort today, but it does require us to be thoughtful and deliberate, because if in fact things do start taking off in the next couple of years, the last thing we want to do is all spend our time chasing after the precious few graduates from quantum information science programs and competing against one another for that talent. Okay, so no talk would be complete without a little bit of an overview of what we do here at Deloitte. We are happy to help you anywhere you happen to sit in the journey, whether this is talking about getting ready from a cyber perspective. I touched briefly, and I'm happy to talk at more length about some of the implications of the future of cybersecurity, of quantum computers, and what we need to do today. A lot of that, I would simply say, is the most important thing to remember is good cyber hygiene goes a long ways. It's as much fun as flossing your teeth, and yet it is not possible for somebody to decrypt data they do not have. So thinking about how do we continue to do the right things to keep things secure, and how do we make sure we know what we have and how it's secured today to be ready for the transition of tomorrow, that's a lot of what those services are about. We are happy to help you with strategy and roadmaps, planning, wherever you are in the journey, whether it's training and education, whether it's thinking about workforce readiness, whether it's understanding the sets of use cases and what you might be able to use this technology to do. All of those sorts of things we are happy to help you with, because we understand that that's a lot of where people are as they think about getting started. And then certainly, if you are ready to go implement proofs of concept, if you want to do research, if you want to think about implementations and other things, we are more than happy to help you with all of those things. We have a group of quantum research scientists, quantum data scientists, physicists, chemists, mathematicians around the globe working on these problems all the time. And they love sinking their teeth into people's real problems, in addition to all the other really remarkable stuff that we collectively come up with. So with that, I think we've got some time for questions. So maybe I will take a deep breath and see if that generated any questions, or if people would like to hear about cybersecurity or other things. Happy to go from here. And let me see, I can maybe open the chat and see.
Yeah, I was going to say we did have a question in the chat.
Sure. So Arthur asked, who do I believe will build the crypto analytically relevant quantum computer, sovereign nation, commercialization, or academia? Sometimes what I tell people is, if you measure my ability to predict the future based on my stock portfolio, I would simply say you should take everything I say with large grains of salt. But Arthur, what I would suggest is that it is not likely that academics will be the first ones to build the large-scale computational infrastructure that's required due to the size of investment that's needed. After that, trying to speculate whether or not that will be a supercomputing machine, a photonic machine, an ion trap machine, a topological qubit machine, built by any particular organization or by a sovereign nation or what have you. The challenge that I remind people of is it is easy to predict, or reasonably easy to predict, changes that are being made through improved engineering, because that tends to be a predictable process. A number of the problems that these technologies have today, particularly as they scale, is that they become research problems. We're not actually sure how to solve all the problems. It is much harder to predict research breakthroughs than it is to predict engineering results. And so some of the challenge in the space of predicting who and when and how is that it counts on people's intuition about the progress of research, not just the measurable, demonstrable progress we can have around engineering. So hopefully that answered your question. And I think if people have questions, given the way the recording thing is working, unless you're in the browser view, you might have to put them in chat. So. Quantum and AI integration, Joe's asking, via various vendors, are there a solution for best fit just a few large players, or is there room for small business? So the good news in all of this is there is room for small business. In fact, most of the quantum community at the moment is a collection of small businesses and startups. Many of them are people who come out of academia. I know of a number of others who are simply people who are passionate about the technology. They are, in many cases, the ones who are advancing quantum and AI, the intersection of those two things together. And there's a whole range of those things that are going on. Just for fun, right? Because I realize I've gotten through this entire talk so far without talking about generative AI. You can actually use quantum computers in generative AI purposes as well. So they will not be running the large language models that many people are familiar with. But what sometimes people don't appreciate is there are lots of other types of generative AI. We've actually been exploring the use of what are called quantum generative adversarial networks. That's a super fancy title for a somewhat complex topic, to actually do medical image generation. So for now, it's still a little bit of a prototype, but the way it works is you actually set up two machine learning models that are basically training one another. And one of them is basically training the other one until the point where it can generate images that are good enough that they pass for the real thing. It turns out that if you think about medical image data, there is not a lot of it available. And so being able to generate synthetic images becomes a really important problem. That's a generative AI problem. It may actually be incredibly tractable to quantum computers in ways that are super interesting. When we work with clients, what are the key pain points in organizations with existing quantum programs that we see? I think a lot of organizations at the moment who have existing quantum programs, there's a variety of challenges that start to happen. One of the biggest challenges is the existing programs tend to be trying to plan for the future. If you are a global financial services organization, there are a lot of pressures day to day to actually accomplish things and get things done. Many of these technologies are not yet ready to be competitive with 60 or 70 years of experts working at classical computing. So the challenges tend to be sort of this combination of things. First, finding the right people. Second, getting to the technologies to the point where you know where you're going to be able to use them somewhere in the organization. And then third, walking the balance of the promise of the future and the need to wait. Some organizations are more comfortable speculating on things that are going to take time to achieve. Many organizations are incredibly short-term focused, and that makes it complex and complicated to continue to justify why we're doing this when it's not going to impact next quarter's earnings. And so I would say, a lot of what people can do is there. AJ asks, what can forward-thinking companies do to get ready for quantum? What I think a lot of organizations can and should be doing is looking at the list of use cases that they have from a business perspective and saying, if they're in optimization, if they are in artificial intelligence and machine learning, if they're in and around the simulation of sort of the physical reality we live in, what could we do to do these better? Or perhaps I should say it differently. If we could do one of these things materially better, where would it make the biggest difference? And the reason for asking the question that way, and then thinking about how we inform it with what we know about quantum computing, is because at the end of the day, the things that are going to be worth exploring the most and worth spending the most time on are the things that are going to add the most value. They might be the things that are the most challenged today. They might be, I'll give you a different example. If we think about insurance, most insurers have a small number of claims inspectors. So I submit a claim. In some cases, not every claim can have a human being go out and inspect whether or not it's true. But knowing that there is a certain amount of fraud in the insurance industry, what you want to do is figure out what are the cases most likely to have fraud and go identify those so you can prioritize sending somebody to look at them. Doing an even slightly better job at identifying those use cases makes a material difference to the insurer. For a variety of reasons, not the least of which is it reduces the overall volume of fraud as people know that they're more likely to get caught. So being able to figure out where are those key places where somewhat better machine learning predictions might give you a better outcome, those are places to go and look. What I would also say is if that seems like a lot to do, you can always phone a friend. We here at Deloitte are more than happy to help with that problem. A lot of others are willing to help with it as well. So speaking of cybersecurity, would it be easier to make data disappear instead of using quantum technology to protect it? So Andy, what I would actually say is, what's interesting is most organizations are afraid these days of deleting information. And we've been going on this idea that storage is cheap for the past decade or so. And part of what winds up happening is when we have the perception that storage is cheap, there's a temptation just to save everything just in case and just because, as opposed to stopping and asking the question, just because we can, should we? So part of what's going on is, I don't know that you can necessarily make information disappear, But if you do the inventory of all of the information that you have, you are likely to find that there is stuff that you're keeping that you probably don't really need, and that you might actually just be better off deleting so that it's no longer useful, accessible, viable, on your nickel, right? Part of your liability or anything else. And I don't know if you consider deleting it, making it disappear, but certainly I would say that that is a way to think about it. Tim asked, understanding we need to take it with a grain of salt, what are the first few example problems I believe quantum computing is likely to tackle, and rough timeframe estimations? I suspect that the places we will see the nearest term things are likely to be in the area of machine learning, and they are likely to be in cases where quality of results is more important than time to result. What's a good example of that? Well, if you think about my insurance example, if you're an insurer, getting the right group of claims to go inspect is probably more important than whether or not it happens really quickly. Conversely, if you're a financial service organization processing credit card transactions, in real time, you don't have the luxury of slowing down dramatically to pick the right ones. You only have a small amount of time to make that decision. So more likely insurance in that case, insurance claim selection, than perhaps real-time transactions. But if you are a large financial organization with a lot of historical data, and you're wondering where else might there have been fraud, that might be a really good case. Because what you're doing is you are asking a prospective question. The time is not as important, but the quality of result is. There are probably other cases we could think of, but I would say a lot of it is probably in this area of quantum machine learning. A lot of quantum machine learning is really this idea of classification. Classification is the idea we break things into maybe two categories: things we're worried about and things we're not worried about, as an example. Those are good places to go and look. The only other place that might be, that I can think of, would be in some of the optimization use cases. Trying to find a better way to route our fleet. Trying to find a better way to pick who's going to be on duty when we have a very large workforce that is very dynamic and hourly. Maybe it's trying to manage very complex logistics, predicting where we're going to need things at what time. I suspect those are the kinds of problems we might see that people tackle first.
Any other questions? I don't think so. Yeah, thank you so much for the great discussion, Scott, and thank you everyone for attending and asking such great questions. Also, thank you for remaining patient as we dealt with those recording issues. Hopefully we can fix that for future presentations. But Scott, thank you so much, and we hope to have you again in the near future as the quantum information, I guess, industry as a whole continues to develop. We hope to have you back and get an update on the latest and greatest. But thank you so much.
It's been a pleasure. Thank you all for the time and the attention and the great questions. And yeah, next time we'll figure out all of the lovely Teams recording stuff.